Uh, Good afternoon and welcome everyone. Today, this is Chahel here from Programming Club of IIT Madras, and I will be taking a session on Sieve. This will be the part one of the session, and the second part of the session will be taken by my friend Charan, who will cover vectors and pairs of STL. Uh, so, in this session, we'll try to cover. We'll give a first introduction to Sieve. Then we'll cover the implementation of Sieve, how to implement it, and the various optimizations that we can do to the Sieve to make it faster. And then I'll try to teach segmented Sieve to find the prime numbers between a given range. And if time permits, I will solve the code forces problem of T primes. So the basic problem that Sieve is used to solve efficiently is to find all prime numbers, say up to a certain number n. And the basic algorithm is the same one that we had studied in elementary school, in which we basically take 2, strike off all its primes, and then we take the next prime 3 and then strike its primes, and so on till all the primes are covered and all the composite numbers are striked. And we do this up to n, so eventually we get the required sieve. So I could give you a demonstration of it, as like we can say our first prime is 2 here, and then we strike off its multiple 6, 8, 4, 10, and so on. And then we take, say, the next prime number 3. So we could go on striking off its multiples in the same way. We could strike 6 first, then 9, and then so on. We'll strike 12, then 15, and so on. We'll keep striking off. I'm doing this up to 50 so that you can get a decent idea of how it works. So first we have done it for the multiples of 2, as you can see, and then for the multiples of 3. So 27, then 30 is already striked off, then 33, and then 36 is striked off, then 39, then 42, then 45, and 48 is already striked off. So that's what we did for 3. Now we'll do the same for 5. So one thing I'd like you to notice is now we are striking to strike off for 5. But if you see the first prime number that is not striked off for first number that is not striked off for in multiples of 5 is 25. And if you see any number less than 25 that is a multiple of 5 is already striked off. So we'll start this from 25. We'll strike off 25. Then we'll strike off 30. Then 35. And then we'll strike off 40, which is already striked off, and then 45, and then 50, which is already striked off. So that's what we did for 5. And now if you see for the next prime 7, so you will notice that again the first non-striked off multiple of 7 is 49, because all the multiples before it, say 14, 21, 28, and 35, and 42. All of them are striked off already. So the first number that we are striking off here is 49. And then now we'll do the same for 11, but then we'll notice that there are no unstriked off numbers for 11 till 50. And same for 13, there are no unstriked off numbers, and so on. So what we basically get is that the unstriked off numbers right now, they are our required prime numbers. And this is the basic algorithm of Sieve, and this is what we had done in the elementary classes. Now, just to notice like what this basic algorithm, how we'll implement it sort of. So what we are doing is we are starting from I equal to 2 till I equal to, say, I less than n. So first our I is 2, and we are doing this iteration up till I is less than n. And what we are doing is we are say we set up like first we initialize an array such that its size is n and all its entries are 1. So what this array will do is it will store whether a number is prime or not. So if a number is prime, the array will have value 1. If it's not, then it will have value 0. Basically, 1 will show that the number is not striked off yet, and 0 will show that the number is striked off. So our array of n is initially all values have been initialized to 1, and then we start off from value 2. And what we do is for I less than equal to n, we check whether array of I is equal to 1. Like, so this basically checks whether the number that we are at is prime. If it is prime, like this is an if statement. If it is prime, then we strike off all its factors, all its multiples, sorry. Now say the number that we are at is not a prime number, so it is a composite number, say 4 or something. Then in that case we don't need to do anything because all its multiples will already be striked off by lower prime numbers. So this is all we need to do, and we just need to iterate over I over 1 to n, and that way we'll be able to construct our sieve. Now we need to try to write the code for this process of how to strike off all its multiples. So for this, what we'll do is we'll start from I equal to, we'll make another variable, like this can be a function or we can implement it either ways. So we'll make another function j with or a for loop, which will have j equal to 2 into I. So basically the smallest multiple of any number that is not striked off will be double of that number. And we'll implement and j should be less than equal to n because we are striking off only till n, and j should increase by I. Basically, why should j increase by I? Because if you have any number, then its multiples are all have a difference of that number. So that way, this j will go over all its multiples. And what we'll do is we'll just set array of j equal to 0. So this will denote that the number has been striked off. And we do this recursively till we reach n. So basically what we did is, for say in this case our n was 50. Initially in first iteration our I was 2. So we took I equal to 2 and we striked off all its multiples, as you can see, till 50. And then in the next iteration, 3 is the first unstriked number. So we took 3 and we striked off all its multiples, as you can see. 3, then 6, then 9, then 12, and so on. So that way, what we are doing is we are basically striking off the numbers in that way. Now we will try to implement this on C++. Like, or first wait, I'll discuss the various optimizations that we can do to this code. So this pseudocode. So basically, one of the key observations that we made while striking the numbers off is that for any prime p, like say if p is a prime number, then its first unstriked index is at p square. Now, why is this so? Because basically, if say we take 2, then all of its say the first unstriked number is 4 in that case, which is obvious in 2's case. If we take 3, then it was obviously 9, because what is happening is if there's any other multiple of p which is less than p square, so that will be of the form p into k, something like that, and k is less than p. However, this number k will either be a prime or a composite number, and it will have smaller prime factors. So what will happen is that by the time we reach p, this number would have already been striked off. So we'll have to start a striking process only from p square that way. So that way we'll start only from p square and strike off. And that's how we'll proceed, and that's the first optimization that we make to our sieve, because basically what we are reducing the number of iterations by j using this process. And so this is the basic algorithm of how we'll implement the sieve and how we'll do the first optimization to sieve. If anyone has any doubts in this, you can put it in the chat. Yeah. I'm assuming there are no doubts, so we can move on to the implementation of sieve and how we'll write the actual code for the sieve. So here it is. So basically we have included the library and use this part of the code, and we have type def long into ll, and that way basically whatever because the numbers that can be given to us can be very big, and we need to calculate whether they are prime or not very fast. So that's why we are using the long data type. And now so basically to store all the primes up to say any number, we'll first make an array, and we'll make a boolean array because we only need to store 1 or 0, nothing else. And we'll set this array as a bool of prime, and this will have a size of say, let's say 10 power 7, because that's the largest size that we can declare. So yeah, so we have set up an array of 10 power 7, and now we'll make a function sieve. So we'll make this a void function because we don't need to return it, because this array has been globally declared, and so we can utilize this array anywhere in our code, and that won't be a problem. So now we make a void function sieve, and the input to this function will be a number rn, which is the number till which we have to calculate the sieve. So this is our number n, we have taken it as input. And then so now I want to teach you an interesting operation, like an interesting function that wouldn't have been covered before, which is Mem Set. So this Mem Set function, what it does is it initializes the same value to all the bits of the data. So for example, in this case, what I wanted to do is that I wanted to initialize all the values of prime as 1. Now I can't do that directly by equating it to 1, because that's not how C++ syntax allows it. However, there's this function called memset, and what this function does is that in the first parameter, you give it the element, the variable that you want to change, and then you write the value that you want to change it to, and how many bits of it do you want to change. So what this function does is it takes every bit of that variable and changes it to this value in the middle. So in this case, we have changed every Boolean number in prime to 1. So that way we have initialized all the values as uncut. Now the trivial ones, we'll first strike off 0 and 1, because those are obviously not prime numbers, as we already know. And so that's what we are doing now. All right. So now we move on to the loop part. So as we could see here, what we'll basically do is we'll go from I equal to 2 to n, and then this is the first outer for loop. So that's what we start to implement now. So we'll make for ll. We are using long because numbers can be big, so just to be safe on that part, and it's more comfortable to use long data type than int data type, because you can uh, use it anytime. So okay, I see a doubt in the chat that bool prime equal to 1. So basically that doesn't work in C++, only you can initialize to 0. So I'll show you that once. Wait, okay, I don't need to comment these. So I've set the prime array to say 1 this way, and I see out say prime of some big number. All right, and if I run this, wait, just a minute. Yeah. Yes, I'm getting output as 0 only, even though I've initialized it at 1. So basically what happens is to initialize every element as 1, what we'll have to do is we'll have to do 1 comma 1 comma 1 for 10 to power 7 times, which is clearly not efficient. And if we do just 1, then I think it just initializes the first variable to 1. Like, yeah, see, only the first element get initialized, and rest all elements don't get initialized. So that's why we need to use Mem Set in this case to set all the values to that. I hope the doubt is clear now. So now that we have initialized 0 and 1 as strike numbers, now we start from 2. So LLI equal to 2. And now our condition is that I should be less than equal to n. And we are increasing I in steps of 1.
Told a story that happened in this area hundreds of years ago. It was a happy village, but since a girl named Apaga
Shlok, please mute.
People in the village are suffering from a strange disease one after another. The whole village fell into a panic to eliminate.
Can you please mute Shlok Verma?
Then throw torches at the house. At the same time, the whole village began to relocate. None of them know it.
Chahel, you can use the mute all
Yes.
participants option.
Yeah, I did it. Yeah. Now we move on. So in the code, now that we are this loop will basically go from I equal to 2 to n. So first we'll check whether the I that you are at is a prime number. So if prime of I equal 1, and we'll check that. So one more optimization that we'll make now is that basically we notice that the first unstrike number is p square. So if say we need to strike till 50, we don't need to check 11, because if we check 11, then its first unstrike number will be 121, which is clearly greater than 50. So we need to only check for primes. We need to only do the striking process for primes which are less than root of n. In this case, root of 50 was 7. So we have to do only the striking process till 7, and then that all the rest of the numbers get created as prime itself. So this is another optimization that we'll make, is that we'll go into the striking part only if the number is less than root of n. So this is how we check for less than root of n. And then we'll go into the loop, and now we'll start the striking process from here. So the first number that we'll strike off will be square of I. So that will be I into I in this case. And we'll have to check that we'll strike till up to n. We won't strike beyond n. So that's why we'll put this condition. And we'll increase j in steps of I. Because as you could, because because j is a multiple of I. Like j always has to be a multiple of I. We'll only strike out the multiples of I. So if we increase j in steps of I, then only the multiples of I will get striked that way. So that's why we are setting j as this. And then what we basically do is we just strike off that j. So we'll just set prime of j equal to 0. So this way we are striking off the multiples of j, multiples of I, and this will do the striking work. And now this is everything that we need to do to implement the sieve. And basically I'll show you how to say, we'll call this sieve function for say 100. And then we can just output all the prime numbers up to 100 this way, like for LL I equal to 1, I less than equal to 100, I plus plus. And as this is a global array, we can use it in our function as well. So we'll just output if prime of I is equal 1, C out I, and we'll add a space, and we can just run this function then. Yeah, so as you can see, it outputted all the prime numbers up to 100, and we could repeat this exercise for, say, even any number up to 10 power 7, because that's the size of our array. So say we are doing it for 10 power 4. This might take a bit of time. Yeah, but as you can see, we have got all the prime numbers up to 10 to power 4 this way. Right. So this is the basic implementation of sieve and how you'll use it, because this basically helps us to calculate the prime numbers very fast. And now talking about how fast the sieve works, we'll discuss the time complexity of sieve. So interestingly, what we are doing is basically we are taking a prime number p, and we are doing n by p iterations for each p. Why are we doing these n by p iterations? Is basically in this part of the code here. So if any a number is a prime number, then we are striking off all numbers that are its factors up till n. So that will take us n by p iterations for any prime number p, because we'll have to, like, roughly n by p, it will be a bit less than that, but as a order of magnitude, as Sean might have told you, that we do estimate. So we'll only take n by p p iterations of this loop, and the outer loop will keep running for each prime that way. So basically that way our time complexity will end up being sigma n by p of I, where p of I is ith prime number, and we'll do this summation from I equal to 1 to some number k, such that p of k is less than equal to, is the greatest prime less than n. So this would give us the time complexity of the sieve. Now this summation is rather hard to calculate, but I will try to attempt that. So there's a well-known fact about primes, that the kth prime is approximately k log k. Now this fact doesn't have a proof as such, rather it has been empirically found by mathematicians. So we'll do this, we'll replace pi by this number, so that's a rough estimate of I, and we can take n out of this summation because n is a constant. So what we get is n sigma I equal to 1 to k, where this pi is replaced by I log I. And now another thing is k is the largest prime which is less than n, but our pk is roughly k log k. So basically what we have is k log k is roughly equal to n. Another fact that we know about primes, this is also an empirical fact, is that up to n, there are roughly n by log n primes. These are only valid for big numbers and not for small numbers, because then only it makes sense, and these are empirical facts. So we'll replace k by n log n then. So basically our summation becomes n sigma I equal to 1 to n by log n, 1 by I log I. And this summation can be calculated by a few analytical methods, and it roughly comes out to be order of n log of log n. So as you can see, the calculations from here to here are rather complicated, but you can look up the time complexity of sieve and you will find them, and you can study those if you're interested. However, as you can see, we are finding prime numbers up to n in just n log n iterations, and that is a very good approximation. The formula of n log n and k log k is valid only for big numbers, so you can't use it for small numbers, because in small numbers the error would be very large and it won't make sense that way. But for big numbers, say we want to find the hundredth prime, say thousandth. If we check for the thousandth prime, let's check the formula for the thousandth prime. So by our formula, the thousandth prime should have a value of 1000 into log 1000. So that will be roughly 3000. All right. Now we can sort of check whether we get 1000 primes by 3000 in our code. And to do this, what we'll do is here we'll keep a counter. So I'll initialize a ll count equal to 0. And whenever this encounters a prime number, we'll increase count by 1. So count plus plus. And we are doing this till 3000. So let's see, up till 3000. And we'll see out count in the end. So this will tell us how many primes are there up to say 1000, up to 3000. So this is just to check that do we get 1000 primes and the formula is roughly correct or not. So if we run this, we get roughly 430 primes. So that means the formula is a bit off, but as you can see, it's a factor of 2, I think. So that way, I guess the formula is not a very good approximation, but it's good for, I think, bigger numbers. Let's try a bigger number. Say we take something like 10 power 6 just to see. So for 10 to power, so like if we take 10 to power 6, say we try to find a 10 to power 6 prime, or 10 to power 5, because 10 to power 6 might be a bit big for my computer. So 10 to power 5. So this will have a value of 10 to power 5 into log of 10 to power 5. Oh wait, I think that is natural log, so that's why the error came. So I have to calculate ln of 1000. So from the calculator, you can see that ln of 1000 is 6.9. So roughly I'll have to do it till 6900 instead. My bad, because I took it as the log base 10. So if I do till 6900, actually the exact number will be 1000 into ln 1000. The exact number is 6907. So we'll do till that and see once, just to check if the formula is roughly correct or not. All right, so let's see. So we get 888. That is still roughly 100 off. Now, say we try to do this for 10 to power 5 once. So 10 to power 5th prime will have this much value, which is roughly this is roughly 1.15 into 10 to power 6. So let's see how many prime numbers are there till this number. And so So roughly we get 89,000 primes. That is about 90% of 10 to power 5. The base and log is E, the natural log. Yeah. So moving on now. So this is how we calculate the time complexity of this algorithm. The calculations are a bit tough, and you can look the details if you want. So now we move on to discuss the topic of segmented sieve. To say, find, like, say someone asks you how many prime numbers are there between 10 power 8 and say 10 power 8 plus 10 power 5. Say, like, you need to find out the prime numbers between these two. Like, you need to output all the prime numbers between these two numbers. So in this case, we'll take this number as our L and this number as our R. So one thing that we'll know is if any number is composite, say a number J is composite, that means it has at least one prime factor. And let's call this prime factor P. So J will always be greater or equal to P square. Because say, like, this is the minimum prime factor of J. So say J is less than P square. In that case, P won't be a prime divisor of J. Like, J would become a prime number that way. So what we basically need to do is to check from 10 to power 8 to 10 to power 8 plus 5. We'll only have to check with all the prime numbers that are less than root R. So we can sort of like take a solvable example of this by say we want to find out the primes between 200 to say 225. We need to find the primes between these two numbers. This is our L and this is our R. So in this case, if we find out root of R, that will be roughly 15. So we need to only construct all the prime numbers up to 15 to check for all numbers between these whether they are prime or not. So all the prime numbers up to 15, if we list them, are 2, 3, 5, 7, 11, and 13. So this will be a set of primes in this case. And we'll just start checking. Say, first we have 200. So 200 is divisible by 2. So that's not a prime. Then 201. So 201 is divisible by 3. So that's also not a prime. Then say we have 202. So 202 is divisible by 2 again. So we can just strike off all the even numbers trivially because they'll be divisible by 2. And we'll just check over the odd numbers. So we have 203. And 203 is, it's not divisible by 2, 3. It's not divisible by 5. By 7, it's divisible by 7. Then 204 is striked off. Then 205 is striked off. Then 207 is striked off. So because this is divisible by 3. Then 209 is, this is 209 is not divisible by 3. It's not divisible by 5. It's not divisible by 7 either. If we check with 11, yeah, it is divisible by 11. Next, say we take 211. This is not divisible by 3, it's 5 or 7. It's not divisible by 11 either. If we check for 13, then it's not divisible by 13. So this is a prime number. Then say we check for 213. So divisible by 3. 215 divisible by 5. 217. This is not divisible by 3. Not divisible by 5. Divisible by 7. So this gets striked off. Then say we check for 208, 219. So this is divisible by 3. So that gets striked off. Then 221. So it's not divisible by 3, not by 5 or 7. By 11 also, it's not divisible by 11 either. If we check for 13, then 1/3 is divisible by 13. Now, if we check 223, this is not divisible by 3, not divisible by 5, not divisible by 7, not divisible by 11 either, and not divisible by 13. So this is a prime number. And then 225 is obviously divisible by 5. So this is not a prime number. So these are the only two prime numbers that we found in this range. And we'll just check this out once whether we are correct or not. So we'll call sieve of 225, and we'll start this from, say, we need from 200 till 225. And we'll see out if we get any prime numbers in this case. So yeah. So we'll run this once again. Yeah, so as you can see, 211 and 223 are the only prime numbers that we get in this range. And so that tells us that our algorithm is correct. So now to implement this algorithm, what we'll do is we'll make another function of seg sieve. Or wait, I'll do that on the next page for clarity. So we'll make a function called segmented sieve, and we'll pass two numbers in it, L and R. And basically what we'll have to do is we'll calculate a number, say t, that is root of R, and then we'll call sieve of t. So sieve of t will generate all the prime numbers till root of R. So now that we have all prime numbers till root of R, what we'll do is for I equal to L, I less than equal to R, I plus plus. So one optimization that we can do here is that we do I plus equal to 2, because all all multiples of 2 will already be striked off. But even if we not do that, because it's pseudocode, so here what we'll do is we'll go from L to R, and we'll check for, say, for j equal to 0, j less than equal to t, j plus plus. So basically what this is supposed to do is that we'll go over j and check if j is a prime number. So if prime of j equal 1, then what we'll do is we'll check whether j divides Ri. If I percentage j equal 0, first, actually, my bad, we'll initialize an array here, say an array of size r minus l plus 1, and we'll initialize this to 1 using the same mem set that we did last time. So this array will store whether any number between L to R is a prime number or not. And what we'll basically do is here, so j is a prime number, and if j divides any number I, then the array element corresponding to that will be array of I minus L, and we'll set this element to 0. So that way, if we run this code, then all the array elements will be initialized to, we'll basically do a segmented sieve that will initialize all the array elements to 0 if they are not prime, and if they are prime, then they'll be set as 1. This is basically what I've illustrated here. The implementation of segmented sieve in C++ is a bit complicated, and you'll understand it better if you know vectors, because that way we won't have to iterate over all primes. So it improves our efficiency that way, because we'll only create a vector of all the prime numbers, and we'll iterate only over that vector. So that way our space and time get saved. Charan will teach about vectors, and after that I'll upload the code of segmented sieve and you can see that. Now moving on, we'll try to solve a code forces problem using the concept of sieves. So this is the problem. So as you can see, it says that prime numbers are positive integers that are divided only by that have only two positive divisors, which is the definition of primes. Now they have devised a new term known as T primes. So a T prime is a number that has exactly three distinct positive divisors. So that's a new type of number that they have defined. And now they are giving us an array n, and we need to tell whether they are T prime or not. And you can see they'll give us up to 10 to power 5 numbers, and each number can be as big as 10 to power 12. So basically, if they give us any number xi, and we need to check whether this number is T prime or not. So if we and to be T prime, it has to have three factors only. So we know that the number always have a factor of 1 and the number itself, but it has to have only one more factor. And if we have any factor, say if any number n has a factor k, then n by k is also a factor of n. So but we need only one more factor. So if k is not equal to n by k, that will lead to two factors. So that means that k has to be equal to n by k, which implies that k square equal to n. And in this case, k will have to be a prime number, because if k is not a prime, then we'll get more such numbers. So as you have written in chat, that basically what we need to check that xi has to be the square of a prime number, right? So now that we know that xi can be as big as 10 to power 12, so that means that p can be as big as 10 to power 6. Right, because say we take the biggest xi 10 to power 12, its root will be 10 to power 6, and we'll have to check whether this number p, that is root of xi, is a prime number or not. So we also need to check one more thing, that whether xi is a square number or not. So first we will check whether xi is a square number. If it is a square number and its square root is a prime number, then we'll output yes, else we'll output no. In this case, as we can see, 4 is a prime number and its prime factor is 2. So they have outputted yes. And 5 and 6 are obviously not prime numbers. So they are not square numbers. So they won't have a proper square root. And so we have outputted no in those cases. And now we'll go on to the part where we write code for this question. So here we have already calculated all the prime. So we'll use the same code for this. And now, as we know that the prime numbers can be as big as 10 to power 6, so we'll calculate sieve up to 10 to power 6. We'll pre-calculate it. So basically, we are calculating this beforehand. We can't check it for every number as and when it comes, because say if some number is as big as 10 to power 12, and they give us all numbers are that big, so we'll have to calculate the primes. Like basically, see, calculating primes up to 10 to power 6 takes us n log n time, that is roughly 10 to power 6 only. And if they give us, say, these many numbers, 10 to power 5 numbers that big, that will take us 10 to power 11 operations, which is clearly not feasible. So what we do is we calculate it once and for all, and we keep using that for the entire question. So now what we do is we define an integer n, and we take this integer n. So n is the number of times that we'll be given a number. And then what we do is we run a for loop l I equal to 0, I less than n, I plus plus. So this loop will run n times, and then we define another number that is a, and we see in this number that, okay, wait, we'll take the another number as x, and we'll see in this number x. So x is the so as you can see, x is these numbers that they'll give us. So each time we'll get a new x, and we'll have to check whether it's prime or not. So first what we'll do is we'll check whether x is a square number or not. So we'll calculate first a number, say we can calculate a number y, which will be sqrt of x. So sqrt is the inbuilt function in the library, which returns the square root of number x, and this returns a double number. So like basically, as you can see, it will return a double. So a double will have decimal places, but we are equaling it to an integer. So what will happen is that all its decimal places will get cut off, and we'll get only the integral part of the double. Like if say we send in 5 into this function, it will take the square root, it will return something like 2.25, but our y will become only 2 by this. Now we are checking that if y into y equal x. So this basically checks whether the given number is prime or not. So if say it's not prime, so we'll have to go into the else case, in which we'll just say out no. Now say it is a prime number, then we check whether y is a prime number. It's a square number, so we check whether y is a square. So if prime of y equal 1, then we'll see out yes. Else we'll just say out no. So first we'll just check whether this code works. So for that we'll take the test cases, and we know the output is yes, no, no, that we should get. And we put it here, and we run this. So as you can see, we got yes, no, no. So that means the code is working fine. And now we'll just try to submit it. So we have submitted it, and as you can see, it got accepted, and we could do it well within the time bounds and the memory bounds. And so that's how you solve questions with Sieve. And I'll soon make a problem set. The problem set on Sieve is ready, and I'll upload it right after the session. And then you can practice the problems on Sieve. And that's all. Thank you. And now my friend Charan will take over from here.
Yeah,
Thanks.
hello everyone. Am I audible?
Yeah, you're audible, Charan.
Yeah. So let me share my screen. Okay. Is my screen visible?
Yeah, it is.
Okay. So yeah. Hello everyone. I'm Charan. So in the second part of this session, I'm going to discuss about vectors and pairs and as an intro to standard template library. So in this session, I'm going to discuss intro to STL, standard template library, and some key points like iterator and what is auto and vectors, applications of vectors, and pairs also. So let me start with vectors. I'll talk about SQL, what is SQL in the end once it's clear what is vector and all. So vector is like something very similar to an array, but we know that arrays has some fixed size, so vectors don't have any fixed size. So the size is dynamic for any vector. So suppose, let me show you. Let me just. Also, make sure if you are using hash include bit slash stdc++.h, you need not include any other header file. But in case if you are using hash include IO stream, make sure you also include vector header file. Otherwise, like the code won't compile. So if you're using bit slash stdc++.h, it's completely fine. You need not include hash include vector. But if you're using IO stream, do include hash include vector. So for suppose if I declare any array of size 5, let's say, if I want to give some 6 element to this array, I cannot. So because there are only 5 elements that I can put in this array. But unlike this, a vector can take any elements, and by any elements, I'll say what's the maximum limit. But for now, let's say it can take any number of elements. So vector int, this is the syntax to declare any vector. So int represents the data type that you are going to put in the vector. So yeah. To give input, you can declare vector in this way, or if you want to initialize vector with some values beforehand, you can do it like this. So this basically, the second line basically creates a vector of 10 elements, and each element will be 5. So even though I declared only 10 elements, I can still give 11th element to this vector. It's not like it's fixed if I initialize it with 10 elements. Else I can initialize this vector like this. So yeah. So this creates a vector with elements 1, 23, and 4. Now, so this is the syntax to declare any vector. Iterator, let me first, yeah. So how do we give input to a vector? So we'll just remove this. So how do we give input to any vector? We can, just like arrays, you can give it using the indexes. Also remember the indexes are just similar to arrays. So the first index starts at 0 and so on. So you can even do this for int I is equal to less than say 10 I plus plus. You can see input of 5. Otherwise, you have a function to do this, which is the pushback function. If what this pushback function generally does is it puts this element 1, it pushes this element 1 to the vector. So your vector v now has one element, which is 1. So basically now the size of the vector becomes 1. So we can just create a vector now. Yeah. So the first element becomes the first element that you push back. So when I is equal to 0, when I'm running through this, when I is equal to 0, I push back 0. So the first element in the vector becomes 0. next one, next two. So if I see out v of 0, I'll get 0. You can see the output here in the bottom. So that's how you take the input for any vector. Next, we'll talk about how to output the vector. So we saw how we take the input for any vector. So just like arrays, you can do this 10 I plus I plus. You can do this. This will work, but there are some other ways also to how you output some easier ways actually. So for that I need to discuss what an iterator is. So let me go back to that slide. So where I wrote what is an iterator. So iterator is something like a pointer. So iterator points to the element inside the container. So let me give the function. So if you consider v dot begin, so this function returns me an iterator pointing to the first element, which means, so this is like a pointer that is pointing to the first element. So iterator is used to iterate through the array. And how do you declare an iterator? Vector int iterator id. So this is like the syntax for iterator. It looks complex, but then when you get used to it, it's completely fine. Till now, any doubts actually? Um, okay, I think fine. So iterator basically iterates is used to iterate through the vector. I need b dot begin is a function which returns the iterator to the first element. So if our vector is 1, 2, 3, 4, v dot begin. So let's say v dot begin is here. It returns an iterator or a pointer which is pointing to the first element. Just remember that v dot begin is not the first element, it's just pointing towards the first element. And v dot end points to the element next to the last element. This is also like some important point because v dot end does not point to the last element, but it points to the element that is next to the last element. It's this is not an element, it points next to the last element. That's it. So you cannot actually print v dot begin because it is an iterator. But if you want to print what is at the at v dot begin, like what is at this position, so you need to use star here. So this prints what is at v dot begin. So if you want an iterator which is pointing towards the second element, you use v dot begin plus 1. So this points towards the second element. So if you want an any iterator which points towards the ith element, so it is v dot begin plus I. So this returns an iterator pointing towards the ith element, ith indexed element in the vector. So if I is equal to 0, we are getting the first element with, the index is 0. If I is 1, we'll get the second element, that is the element with index 1, and so on. So now for iterator is equal to v dot begin. We're starting at the first element. Now we want to print the entire vector. So I'll just explain it after writing. So yeah, our iterator starts at v dot begin. So it basically starts at the first element, and now it prints star it. As I said, you cannot print v dot begin. To print the element which is at v dot begin, you need to use this star. So cout star it and l. This just prints the first element. Then iterator plus plus. So iterator increments by 1. It gets incremented by 1. So we now it points towards v dot begin plus 1, which is the second element. Now it prints the second element, and it goes on till iterator is not equal to the end. So when iterator becomes equal to v dot end, then the loop will end. So this also prints our entire vector. We'll just run this. We'll remove this. Yeah, as you can see, it prints the entire vector. Next, by the way, is the output visible clearly? What is the difference between a linked list and a vector? Yeah, I'm not sure. In ith element, I starts from 0 or 1. 0. Yeah, as I said, I is the index here. Here, I is the index. It's not the element number, it's the index of the element. Yeah, is that clear? Tanmay, is that clear? Yes, but then there are some differences between iterator and pointer. You can just look at them. I don't think I can explain all that in this session. Yeah, but true, iterator is basically a pointer. That's fine, right? Okay. Next, next we'll talk about the auto keyword. Auto. So instead of declaring iterator using this big syntax, you can just use this keyword auto. So what auto basically does is, so if you declare auto I, let's say, is equal to 5, it automatically like the code automatically takes that this I is of type data type int. So you no need to mention that I is of type int if you're using the type auto. It automatically takes the data type. So for iterator also, you can do that. For auto I is equal to v dot begin equal. remove this. So this also works. So the code takes that IT, so it generally sees this v dot begin and knows that this is an iterator. So it will automatically consider IT as an iterator for a vector int. So even if I remove this, even if I comment this out, it will work. Yeah. Next, another way of printing uh, the vector, like this is the most easiest way to print it for auto I in V. So what this means that for every I in V, in for every I in the vector V, print I. So it will print all the int elements in the vector 0 to 9. Yeah, like this is the easiest way to actually print any vector. Now we'll see some basic functions. Any doubts? Okay. Yeah, Tanma, you can unmute or
Can you explain the second use of auto keyword?
this one.
Yes.
Yeah. So for every here auto means, so you can, okay, let me, for every I in V, so V is a vector, right? So for every I in V, we are printing out I, which means if you write in here, for suppose, we know that vector V is of int type, right? So for every integer in vector V, we are printing out that integer. So this for loop means that, so instead of writing int, you can also use auto, because auto will automatically, it will automatically detect what data type it is of. So that's it. You got my point, right?
So can we also print float or double type data also?
Yeah, we can. Let me. So you're asking in the vector or in
No, no,
general?
this vector.
No, you cannot, because vector v is of type int, right?
No, if we define it as double
Yeah, you can.
initials.
Yeah, you can. So if you use auto word, you need not mention int or double or char anything.
Okay.
Let me do that as well. We'll use float. Um, we can use, see, you can use this for float or double. Also, auto keyword automatically takes the data type irrespective of like it's int or char. You can use this for char, string also. Next, we'll see some functions, some basic functions in vector. Okay. Yeah, these are input and this is about output. I discussed them already. Yeah, we'll talk about size and capacity. Take the previous vector. Okay, as I said, vector automatically resizes itself. we'll see what is the size of the vector here. So b dot size. So this dot size function returns the size of the vector at that moment. So let me print the size of the vector here. Will not print. So if we see the size of the vector, it's 0 here. After we push back 10 elements, the size will be 10. So yeah, the size will be, it was 0 initially, and after pushing back 10 elements, it's 10. So this, by this we can say that it automatically resizes itself. Now let me talk about another function, cout v dot capacity. Size here. We can see that the size was 0 initially and now it's 16. So what is the difference between size and capacity? Let me just clear all this. So how vector works is, initially the capacity of the vector, so the number of elements it can take, was 0. Now if we push back one value, the size becomes 1, whereas the capacity becomes 2. The capacity is like the maximum number of elements it can take at that moment. So it's 2. Now when you push back another element, when the size becomes size, capacity. When the size is 2, the capacity remains 2 because the vector can take 2 elements. Now when the size, when you add another element, what the vector does is it creates another, like, array, let's say array of size 4, copies the first 2 elements and pushes back the third element into this array of size 4. Now like this is basically 2 powers, so this is basically 2 square, this is 2 power 1. When you push more than 4 elements, now it doubles, now the capacity doubles itself and it becomes 8 now, and so on. So here, since there are 10 elements, the capacity is 16. So if there are n elements, the capacity would be the nearest 2 power greater than n. So I mean, nearest 2 power greater than n. This will be the capacity of the vector. Is that clear for everyone? Is that clear? I'll take that as an S.
Can you explain once?
Yeah, sure. Just remove everything. So we're talking about size and capacity. So capacity is like the maximum number of elements the vector can take at that moment. So when I said in the beginning, I said you can give as many as elements to the vector. So when you create a vector, memory is not allocated to all the elements. So if you like say if you can put some 2 power 32 minus 1 elements at max in a vector, the memory is not created for all those elements. So the memory is created like when you push back the value. So if you push back one value, so if the size of the vector is now 1, the capacity becomes 2. So what this generally does is the vector creates an array of 2 of size 2 and copies the first element into this array and says that this is your vector. So when you input second element, so this works fine because there is another gap, like there's another place, empty place for your value. The capacity remains same. But when you want to input third element, so this is basically an array. So it cannot take in the third value. So what vector does is it just creates an array of double the size than the previous size. So it creates an array of size 4, copies the first two elements into that array, pushes back your third element to this array, and use and shows this as your vector. Now you got my point. So basically capacity becomes doubled every time. The vector doubles the array size every time you input more than the capacity. Did you get my point now?
So if size is 8, so what would be its capacity?
8 only. So when you try to input another element now the capacity becomes 16.
So we can write like n is less or equal to 2 raised to k.
Yeah. So the capacity is next like uh, the next 2 power which is greater than n. So
But
you-
equality sign should also be there, no?
yeah, equality also will do that. Yeah, equality holds. Yeah, is that fine?
Yes.
Okay. So this generally when you push back one element to a vector, this takes a constant time because it's just you're just giving the input. But whenever the capacity is doubled, the copying of array takes place. So I said right when when you input one element or any number of elements greater than the capacity, what vector does is copies the entire array, the before array, like the previous array, to a new array. So that takes time. So if it is possible, like if you can create a memory before itself, so if you can create so if you want to, let's say, if you want to give 16 elements to a vector, so as I said before, you can create it like this itself so that the memory is created for 16 places before itself. So when you're giving input and when you like cross the limit every time, so it doubles it, so the capacity gets doubled, so it takes some more time than when you reserve it before. So it's always uh, preferable, or to say if you can allocate the memory or allocate the size, it's better to do that instead of pushing it back every time and doubling the capacity. So to do that, uh, to give the memory beforehand itself, you can do this. So this actually creates the size of the vector to be 16. So when you input um, So when you input more than 4 elements, like up till 16 elements, the capacity remains as 16 itself. It won't get doubled. So you'll have some time saved. As you can see, the size will be 16 and capacity is also 16. You can do this, you can reserve the memory in another way also. There's another function called reserve. This does the same thing as this. So what this v dot reserve does is it makes like it makes the capacity of the vector to be 16. Like also observe that v dot size is now 0, but capacity is 16. When you use v dot reserve, when you use the reserve function, the capacity becomes 16, but the size remains 0 only. But when you initialize the memory here, the size is also initialized to 10. And all the elements are initialized to 0. I mean, it depends on the compiler also. Like, is reserve function clear? Yeah, you can ask. Tanmay. Yeah, that is dot reserve function. Okay. Now, one more key difference between vectors and arrays is that you can erase the elements in a vector. You cannot erase the elements once you give into an array. We'll see how to erase. So the function we'll be using is v dot erase. We'll see what are the parameters that it takes. So if you v dot erase takes in a iterator. Remember, it takes in an iterator. So if you write a v dot erase of v dot begin, as I said, v dot begin is an iterator pointing to the first element. So this line basically erases the first element of the vector. So we'll see that. So before the first element, we'll print the first element here. The first element will be v of 0. See out after v of 0. Oh, so once. So this erase function is so this v dot erase erases the fifth element here. We'll just run this. So as you can see here, the fifth element got erased. V dot begin plus 5, as I said, represents the fifth element. So 5 got erased. Some other parameters that it will take is you can mention the interval between which the elements can be erased. So v dot begin plus 5 comma v dot end basically removes all elements from 5 to the end, to the element before the end. So this removes all the elements from v dot begin plus 5 to the element before v dot end. So if, okay, I'll show this. So 5 to end. Just to mention that it does not remove this element. So if you mention v dot begin plus 7, it's not going to remove the 7th element there, because they think it's, yeah, that was some error. Yeah, v dot begin plus 5 comma v dot begin plus 7 will not remove the 7th element here. It will only remove the elements from v dot begin plus 5 to the element just before v dot begin plus 7. Next, we have v dot clear, which just clears all the elements in the vector. So you just don't get anything in the output. Is that clear? Suppose I initialize the vector of size and the memory limit for the question, so I can add only. Suppose I initialize the vector of size 64 MB and the memory limit for the question is 26. More elements to that. Yes, Mayank Mahajan, that's correct. And why was the first element not? I guess that was something to do with the previous code. We can just try it again. Oh, we got clear. Yeah, here we can see the first element got removed. The previous code had something. So yeah, arrays function takes O of n time complexity. It depends on the number of elements you are actually removing. Next, we have insert function. We'll copy this. This makes it easier. So similar to arrays function, we have the insert function. So what this does is it inserts 2 in the position v dot begin plus 1. So if your array previously was 1, 2, 3, 4, now it will insert 2 at v dot begin plus 1. So it will insert 2 here. So our new array becomes 1, 2, 2, 3, 4. If the previous array was 1, 2, 3, 4, now the array becomes 1, 2, 2, 3, 4. We can see the initial vector here is from 0 to 9. So if I insert 2 in the second position, now it just becomes 0, 2, 1, 2. Yeah, 0, 2, 1, 2, 3, 4, 5. You can insert in other ways also. So what this does is this inserts 3 2 times in this position in v dot begin plus 1. Okay. Yeah, it will insert 3 2 times in the starting from this position. So starting from that's important. Starting from this position, it will insert 3 two times. You can also insert elements like this. So at this position, so starting from this position, it will insert 2, 3, and 4. And yeah, it just inserted 2, 3, 4. Starting from the first, starting from v dot begin plus 1. You can like why you can just change this to 5 or something. Still good. Yeah. Next. You can also insert elements like this. So what this does is it starts from v dot begin plus 1, that is the first position, and inserts all the elements between v dot begin and v dot begin plus 4. So starting from the first position, 0, 1, 2, 3, v dot begin plus 4. So 4 elements got inserted, and then there is the vector continues. Yeah, is the insert function clear? Yeah. Next we have empty function. So what empty function does is just returns true if the vector is empty. So here I have some elements in the vector. So vector is not empty. So v dot empty will be false. So if this is false, if v is not empty, then it will print vector is not empty. Else if v dot empty is true, we'll just clear all the elements in the vector and run the code. So v dot empty now returns true. So this line gets executed. So vector is empty. If there are some elements, then it just returns vector is not empty. Now we'll talk about the resize function. So now I have a vector starting from 1 to 10, 1 to 9, 1 to 10. So this is a vector of size 10, 1 to 10, my sorry. Now if I want to resize the vector, if I use dot resize function, now this resizes the vector to size of 5, which means now the size of the vector became 5. It will remove the last 5 elements of the vector and uh, it will print the remaining values. So if I resize this to something greater than 10, let's say we'll resize this to 12, then it will just take the remaining 2 values as 0. We'll just take the remaining 2 values as 0. If you resize it to something less than n, less than the size, it will just remove the last n minus k elements. So if you want to resize the vector to k, it will remove the last n minus k elements. Now we have v dot front and v dot back. Like, don't get confused with v dot begin and v dot end. V dot begin and v dot end return iterators, whereas v dot front and v dot back are the elements. So v dot front is the first element and v dot back is the last element. So these are just uh, yeah. So the first element is 0 and the last element is 9. So v dot front and v dot back represent the first and the last elements. So to access the elements in a vector, as I said, you can use the square brackets as you do for an array. Also, you can use this function v dot et. So these two are basically the same. So v of 0 and v8 of 0 represent the same. So it will just print 0 and 0 space 0, 0. Yeah. Yeah, that's it for the vectors. V dot resize of 4 implies. So now suppose where is the resize template? Check. So if I resize the vector to 4, it means that I'm removing the last 6 elements and just keeping the first k element. So if I resize this vector to 4, I'm just keeping the first k elements in my vector and erasing the remaining all. Yeah. So in this case, it will output 1, 2, 3, 4. So it will just keep the first 4 elements in the array in the vector and will remove. Is that clear?
So last 6 elements are completely deleted or they are stored in the memory.
They are deleted. So if I pay out the size, just 4. Yeah. Okay, I'll remove this to avoid confusion. Yeah, the size is still 4. I'll print capacity also. The capacity is 16, so the capacity did not decrease actually. So yeah, is that clear? So the capacity did not decrease, but the size decreases. Is that clear? So the memory is not deleted completely. Only the elements are erased. Okay. So yeah, that's it for the vectors. After uh, I'll explain pairs now, and after that we'll do 2 problems on vectors. So yeah, pair is comparatively easy and like, let me just write the syntax here first. So as the name suggests, pair int comma int is like uh, we can store 2 values, and I mean we can pair them and store them in a single unit p. So pair int comma int, it represents that p has 2 values, like p stores 2 values which are paired. So the first element is p dot first and will give it 1, and p dot second will give it 8. So a yeah, pair is like pairing these 2 values. So 1, 8, these two can be stored in a single unit. So if they are connected, it depends on the problem. So if they are connected, you can actually pair them. So these pairs can be of different data type as well. So we can pair one integer and one character. Uh, But remember that the p dot first should always be of data type int and p dot second should always be of data type char. So this declaration is different from pair char comma of q. So this is different from this. So in the first case, p dot first, that is the first element, should be of data type int, and the second element should be of data type char. And here the first element should be of data type char, and the second element should be of data type int. Uh, Next, we'll see different ways to pair them and how to print them. So here I'm pairing one integer and one character. So p dot first is 10, so which is an integer, and p dot second is char. I can print them using this dot first and dot second. So see out p dot first space p dot second. This will print 10 space a. So you can pair them. Um, you can also use make pair function to pair the two data types. So here also I'm using int and char. So if you want to make one comma a as a pair, you can use this make pair function also. So this will also work. Yeah. 1a. Yeah, you can also declare it as how you do it generally. So you can declare it like this as well. Initialize it like this as well. So yeah, pair has like nothing more. I'll share the examples using pair because pair has nothing more theoretically, but the applications are wide. And now I'll explain two problems on vectors. So this is the first problem. Like, yeah, any doubts in pairs? Uh, there's nothing much to discuss about pair. Uh, okay. So I think I can move to the question. So I'll put the question in the chat so you can also have a look at it clearly. So you are given an array A of length n. The array is called three-sum closed if for all distinct indices I, j, k, the sum ai plus aj plus ak is an element of the array. More formally, A is three-sum closed if for all integers I less than or equal to 1 less than or equal to I less than j less than k less than or equal to I. There exists some integer such that ai plus aj plus ak is equal to al. So you are given some test cases, and in each test case you are given an array. Now you need to tell if the given array is three-sum closed or not. That means you need to take three distinct elements, I mean three distinct uh, indexes, and add the elements in them, and there should be a corresponding element. So if I take -1, 0, and 1, so the sum will be -1 plus 0 plus 1, which is 0. So 0 is there in the element in the array. So this is three-sum closed. So the output is S. So if I consider the second array 1 -2 -2 1 -3, suppose I consider -2 -2 and -3. the sum is -7, which is not in the array. So the output is, yeah, this is self-explaining, and for this also it is wrong. So any ideas on how to solve the problem? If anyone has any idea, do raise your hand so that. So no ideas how to do the
It's
problem.
basically like almost that if suppose the array will have like if almost all elements are positive, so then if the array isn't three sum closed, so the biggest three elements, their sum shouldn't be in the array. And then similar for the negative one as well, it will be like the smallest three elements sum will not be in the array.
Okay. So what you're saying is if there is some big number, so the largest number, so if we
The
take the
top
largest
three largest numbers, if they're when they're positive,
okay,
it's like their sum won't be in the array.
yes, so yeah, you're correct. So if I
The same
have,
we can do for the smallest three negative numbers, their sum also won't be in the array.
yeah, so if we have more than three numbers, more than three positive numbers, or more than two positive numbers, let's say if I have 1, 2, 3 in my array, I need to make this a three sum closure. If I want to make this a three sum closure, I mean, if I want to make this array three sum closed, I need to have 6 also in this array, and again 11 also, and so on. So if I have if the array consists of more than two positive numbers, it cannot be three sum closed because the numbers should be like will be continuously up to infinity. So more than two positive numbers should not be there. Similarly, more than two negative numbers. So if I have similarly -1, -2, -3, so the sum should be -6. I need to have -6 and again -11 and so on. So I should not have three negative numbers as well. So the number of positive numbers should be less than or equal to 2, and the number of negative numbers should be also less than or equal to 2. What about zeros? Like uh, how many zeros uh, can I take? So one, of course, like the basic solution is that you just need to brute force through the entire array, but of course it will give you TLE, time limit exceeded, because it's not possible. We'll see the size of the array is 2 into 10 power 5. So brute forcing this equation is not at all correct. So now we've decreased the number of elements. So if there are more than two positive numbers, we'll output no. Similarly, if we have more than 2 negative numbers, we'll output no. Now, what about the number of zeros that we can like have in the array? Anyone? Suppose if I have -2, -1, some 10 power 4 zeros, 10 power 4 zeros, and 1, 2. It's not possible to brute force through this entire array again, right? So we've decreased the number of positive numbers to 2, number of negative numbers to 2. Now, what about the number of zeros? So what to do if we have some 10 power 4 zeros in between?
We can consider it as like 1 0 effectively.
We can consider that as 1 0. Yep.
Because irrespective of like number of times you repeat the zeros, they'll have the same thing in the sum, right?
Yeah, yeah. So okay, let me just think of one example. Like, what if I have this array 0, 0, 2? So I take 1, 0 and 1, 2, but this is actually what is it? This is some closed one. What?
I guess the person has switched on his mic by mistake. You can mute him.
Okay. Yeah, where is the Okay. If there is 0, the number of positive numbers is found. Where here.
Actually, it isn't, right? Because like 1 plus 2 plus 3 isn't in the array. Same for -1, -2, -3. Their
Yeah.
sums aren't in the array.
Yeah.
So it can't be 3 sum closed.
Yes. So okay, Tanmay says it is 3 sum closed. Tanmay, it's not right because the sum of 1, 2, 3 is not in the array. Yeah, so to avoid this problem, so if there are only three elements in like this 0, 0, 2, then if we consider these two zeros as a single zero and 0, 2, you cannot even run through the array. I mean, you cannot brute force the solution.
Maybe you can keep some sort of a thing like if the number of like positive or negative elements is a positive and negative elements, both of them they are like less than 2. So in that case, we can consider like the number of zeros as such in their total numbers, because this ends up being a corner case which we didn't account for in the beginning.
Yeah, so instead of like separating them for all cases, we can just take the number of zeros till they are 3. So like the corner cases would be something like 0, 0 and then one number and 0, 0, 0. For these two cases, we'll just say we'll take the number of zeros till 3. So oh. So you got my point, right? So for any array, we'll just take 3 zeros into the. We'll consider 3 zeros. If there are more than 3, if there are less than 3, then we'll take only those numbers. If there are, let's say, if there is only 1 0, we'll take only 1 0. So if there are any number of zeros greater than 3, um, we can just erase all of them and just take 0 only. Is that fine with everyone?
Could you please explain that part again? It wasn't audible.
Yeah, one. Yeah, Tanma, wait 1 second. I'll just explain this once again. So the corner cases are like 0, 0, like the corner case where you cannot consider the number of zeros as 1. And then there is one number, any number x, and 0, 0, 0. Like, of course, this comes under this, but considering this, if we take the number of zeros as 2, like, then we'll miss this case where there are only 3 zeros in the array. So like to miss any case, we'll just say if number of zeros in the array are greater than 3, greater than or equal to 3, then we'll consider 3 zeros only. So otherwise, we'll take the number of zeros as it is. So if there is only 1 0 in the given array, we'll just consider 1 0. If there are 2 zeros only, we'll consider 2 zeros. So is that fine now?
Understood. So if there are more than 3 zeros, we'll consider it as 3 zeros. But if there's
Yeah.
1 and 2, we'll consider them as like 1 and 2 zeros.
Yeah.
Understood.
So 1, 2 minus 1, 2 is there. So -2 is there. Yeah, it is threesome enclosed. Yeah, it is threesome enclosed. Yes. Yes, Tanmay. But every threesome need not be in the same form, right? Like in A, B minus A minus B form.
This is one case.
Yeah, yeah. If it's one case, fine. Okay, let's just think about the code now. Um, suppose, yeah, now we'll create two vectors. One vector for positive numbers. Yeah, I have the code actually. We can look at it. Work. Yeah. So I already wrote the test cases part here. So we just need to find out what's inside for every array. The first line contains the first line of the, yeah, first line of each test case contains the length of the array they will be giving. So input n, c input n. For I is equal to 0 to n, we're taking the input for, we're taking the integer value. If it's greater than 0, we're giving it to the positive. This is the vector POS. We're pushing it back to the POS. If it is less than 0, we're pushing it to negative. Else, if it is 0, and else if it is 0, we're pushing it back to a dot pushback. So we're pushing it back to a. So what this line does is, if the size of a is greater than 3, that is if the number of zeros in the given array are greater than 3 or more than 3, then it won't push back anything to the array A. Let's consider this array A is actually the final array we will be considering, the array with two positive numbers, two negative numbers, and we'll consider that array as A, the final array after this simplification. And before that, we have one positive array and one vector which takes all the positive values and one vector which takes all the negative values. So like, look at the use here. Like, we don't know the number of positive numbers that we'll be having in the array beforehand, so we are using we're using a vector here. So as we can push back as many values we can, and for x less than 0. So is everyone like clear with this part? Else if a dot size is less than 3, like, everyone clear up till this part in the code? Okay, I guess there are no doubts. Then yes, we can move on. So if POS dot size, that means if there are more than two positive numbers or more than two negative numbers, we'll print no, and then we'll move out of the, like, we'll just return the function. So this is a function I'm writing, solve. So we'll just return the function. So after this line, if the positive numbers and negative numbers are less than or equal to 2, then we'll push those values to A, because as I said, A is like we'll consider A as the final vector after all this simplification. So we'll have these values in A. Now I'm just brute forcing the solution AI plus AJ plus AK is equal to AL. So I'm just checking if for every a, I, a, j, a, k, this is true. If this is not true, then I'll print if exclamatory mark okay becomes so if this is not true, I'll print no. So for at least one triplet ai, aj, ak, if I couldn't find ai plus aj plus ak is equal to al, if I couldn't find any l like that, then I'll print no. Else if these loops pass till the end, then I'll print s. Is that fine, the final part also? Okay, yes, it's fine. Yeah, everyone understood the code, right? Just put s if you could understood. You could understand. Okay. So moving on, I have a different question. It's not from Code Forces. I'll just. Okay. So we know that we know the definition of a derivative for variables. So we know d by dx of x is 1. And we also know that derivative of a constant is 0. The derivative, we know that derivative of a constant is 0. So let me define some hypothetical uh, derivative operator for constants. So the operator, the conditions for the operator is that, so d by dx or d by dc or something of c, the derivative of a constant. Let me define this. This is just hypothetical. Is 1 if c is prime. Is 0 if c is 0 or 1. And in when c is equal to composite, let's say c is equal to some d into e. Since c is composite, we can then write the derivative as just like the multiplication rule, uh, d into a derivative of e plus e into derivative of d. So you can see that for any possible combination of d and e, this will be the same for any composite number. So this is here. So for any given number n, find its derivative. So that's the question. You need to find its derivative. So is the question clear? Anyone who could just say if the question is clear or should I explain? Can you send it in a written format? Yes. Right now, like I don't have any return format for this question. I'll send it after the session. So after the completion of the session. So oh, yeah, for now, like, did you understand the question?
Yes.
Oh, okay. So any ideas? So if you couldn't understand the question, just put it in chat so that I can explain to you again. Okay, so done my wait. Yeah, I'll just explain and then give some numerical examples so that will be clear for everyone. So let me define derivative for a constant, for any constant. So if let's say the constant is c, if c is a prime number, then the derivative of c will be 1. If c is prime, else if c is equal to 0 or 1, then the derivative is 0. Else if c is composite d into e, let's say c is d into e, then the derivative is d into derivative of e plus e into derivative of d. So we'll have some examples now. We'll just see some examples. We'll have this also. Oh, okay. Yeah, for suppose if c is 7, then the derivative is 1. So if let's say c is composite, we'll say c is equal to 6. This is 2 into 3. So to find the derivative of 6, you can write it as 2 into derivative of 3. Derivative of 3, since 3 is prime, derivative of 3 is 1, plus 3 into derivative of 2, which is again 1. So this is 5. So derivative of 6 is 5. We'll see one more example. We'll see 12. So 12 can be written as 2 into 6, 3 into 4. Oh, 3 into 4. So we'll calculate using both these notations. So from 2 into 6, the derivative will be 2 into 2 into derivative of 6, which is 5, which as we just saw, derivative of 6 is 5, plus 6 into derivative of 2, which is 1. So this way we got 16. Now using this method, we need to find the derivative of 4 first, into 3 plus 4 into derivative of 3 is 1. So we'll find the derivative of 4. So 4 is 2 into 2. So which is, so the derivative becomes
5. So 4 only.
yeah 4. So 4 derivative of 4 is 4 again. Oh, okay, 4 again. So 4 into 3 plus 4. 12 plus 4, 16. So either way, you'll get 16. So any notation you'll use for any composite number, you'll arrive at the same final answer. Prime factorization, yes. And then so suppose I know the prime factorization of 12 as 2 square into 3. Yeah. What do I do next now? Tanmay, you can like unmute or just type in the chat. Or any other person also can just answer.
This seems more like the sum of the factor number excluding the factor itself. Excluding the number itself, I mean, sorry.
Yeah, but 4, the sum is 4, right?
There's for squares an exception, because for 9 also it comes as 6. It's more like
Yeah.
2 into the square root of the number.
Okay, what about 15? Okay, for 15 also it's like that. We'll take 24. We'll take 24. What about for 24? Is it also the sum of the factors?
Just checking out 1 second.
Yeah.
Yeah, there are quite a bit of cases in some places here.
Yeah, so like that's not actually the case. Your like algorithm or your explanation works if there are only prime factors. So there is no repetition for these prime. So for 6 it will work 2 into 3, and for 3 into 5 it will work only if there is no repetition in these prime factors, then only your explanation works. Otherwise it will change. So yeah, like you are actually in the right direction, so think along the line. Okay, let me tell it then. Suppose our number is of the form A, B, C, D, E, like A into B into C into D into E, and where all of these are prime numbers. Suppose I need to find the derivative of this. So I'll take A as one part and B into C into D into E is the remaining part. Then what do I get? Since it is a prime number, so B into C into D into E into derivative of A is 1 plus A into derivative of B, C, D, E. So again, you can take B as one part and CD as another part, then CDE into derivative of B, which is 1 again, plus B into derivative of CDE. So I'll just write it as CDE whole prime. No, when you expand this, you can observe that the number is BCDE, I mean B into C into D into E plus A into C into D into E plus here we missed A, here B, and now we'll miss C here. A into B into will miss C, D into E. You can actually check that and so on. So the derivative is actually, let n be this number, then what you'll get is n by A plus n by B plus n by C and so on. So if there is a repetition, you just write it in the power of ones only. So in the previous case, while we are discussing 24, which is equal to 2 cube into 3, we'll just write this as 2 into 2 into 2 into 3. Then our A becomes 2, B becomes 2, C becomes 2, and D becomes 3. So the answer will be 24 by 2 plus 24 by 2 plus 24 by 2 plus 24 by 3. Oh, this is
Yeah,
okay.
to come 44.
Yeah, 44. So yeah, this is the logic. So I'll send the question in the format. I mean, as asked, there is derivative of prime power k is yes, the derivative of prime power k is, yeah, this explains why that's true. This explanation, yeah, chain rule can be applied. Yeah, I'll send this in a written format in the slides itself. I'll include this question in the slides itself.
So basically, in this question, the way this question is like, it's like all the prime numbers are like some sort of variables, and the composite numbers, they end up being expressed as like a to the power x or b to the power y, like in some form of powers of these prime numbers as such.
Yeah.
So understood.
Yeah. So I need like I need you guys to actually try this problem. So I set the algorithm. So you just need to code using vectors. This is actually a very good problem to do with vectors. There's actually a nice way to uh, like put how this is here. You need to calculate that 2 is 3 times and 3 is 1 time, and then you need to divide it with 2 3 times. There's actually a very nice way to do that in vectors. So I need you guys to try that. I'll send the question in the format, like in the written format. I'll include that in the slides. And yeah, that's it for today. Any doubts at the end of the session? Okay, I guess there are, okay, there is one. Also code along with the question. Thank you. The ending question was quite good. Yeah, thank you. Also code along with question. Yeah, sure. Like I thought, see, even if I did not code, like the time was up. So I thought it would be enough time for me to write the code in the session. Yeah, next time I'll do that. Like, is that what you want to say? Anuj said.
So actually, I mean that in the slides, when you will attach a question, just for our reference, just try to write the code along. Means just try to mention the code along with your question.
Okay, yeah, I'll do that. Yeah, maybe I'll add it tomorrow just so that people try it today. Okay, is that fine?
Okay, sir, no problem.
Yeah, yeah. Or I'll attach it by today night or something. Yeah, after. I'll just give them some time to just try that. Yeah. So that's it. Bye, guys. Thank you.
You're checking the Prabhu issue. Prabhu is
சொல்லல நான் எதுவுமே பண்ண கீதா எஸ்ஐடி தானே பண்ணிட்டேன் பண்ண முடியும் என்ன ஆல்ரெடி ஓகேவா
on. Should I have to call again? Oh no. Okay, one ticket, bro. Can I close the check ticket? Bye. Okay, bye.